So hi, welcome. My name is Tomer Gabel. I work for an Israeli company called Wix, and I want to thank you all for coming. There's a whole bunch of really good talks concurrently with mine, so thank you. I sort of expected 6 people in the audience, so I'm very much impressed. This talk is going to be more or less an introductory talk about Scala macros. Introductory in the sense that it does not assume that you know too much about macros right off the bat, and it doesn't dig into a whole lot of detail. But then the idea is to give you sort of a sample use case for what macros are good for and sort of drive into the implementation from there. So please feel free at any point to stop me if you have any questions, interject, raise your hands, throw tomatoes at the stage. No, please don't. The cleaning guys are going to be really upset about that. Other than that, you know, if there are any questions, just let me know and we'll figure it out as we go. So to start with, the context here is data validation. That's going to be the use case for macros that is going to sort of drive this whole presentation. And what happened is that we at Wix obviously work in Scala. And as we were migrating from a pretty big heavy legacy code base to Scala, one of the issues that we had was how to do data validation. Now, seeing as our sort of original code base was in Java, we used to use JSR 303, also called bean validation. And that does not really work very well for Scala. So this is not going to be a talk about how to do data validation, but rather I'm going to present one way, one API for doing data validations, and then we're going to dive deep into the macro implementation behind that. So let's get started. I have a dream. In that dream, data validation is trivial to define. So for instance, in this case, what we have is we have a case class, a domain class called person. Very simple class, 2 fields, first name, last name, and we want to define a set of validation rules over that type. So what we started off with at Wix is we wanted an API that looks sort of like this. Okay, we wanted a type class called validator. We wanted to be able to define very trivially a validator over the type of person, takes in a sample object, which I've named P, and then have a very concise DSL for defining specific validation rules on top of that. So just to give you a quick example of what the actual API looks like, if I take this person validator and I use it to actually validate instances of that class person, in case of a validation of a valid instance of person that is a person with a non-empty first name and last name, I get back a success object. Conversely, if I try to validate someone with no first name, what I would get is a failure object. Now, with data validation, what happens is that the failure object sort of aggregates all of the different rules, sub-rules for validation that have failed. And in this case, we only have the one, so we have a set with one violation, one rule violation, and a violation gives you the value on which validation is failed. In this case, it's an empty string. It gives you the constraint that is failed, which in this case must not be empty. And more crucially, it gives you a description of that little bit of data that you actually tried to validate and which failed validation, which in this case is the property called first name. So this is sort of the envelope of the story, what's going to drive us forward. So this is all embodied in an open source data validation library called Accord. It's in GitHub. You're very much welcome to have a look at it and try it out. And Accord is comprises four layers or 4 parts. There's the API, which you've just seen. There's a set of combinators because we're so hip and cool, we couldn't just call them matchers or anything. We needed to come up with a new name, so combinators it is. There's a DSL for defining validation rules, and then there's the macro-based transformation that's going to be the focus of this presentation. So just a couple more things about the API, because that's going to allow us to have a more in-depth discussion about the macro. Basically, a validation takes an object and a validator. It makes sure that the assertions made in the validator apply to that object, and it gives you back some sort of result domain. So the result domain is a simple sealed trait called result. There's two cases for that. One is the success case, and one is the failure case. And a failure case has a set of validations. And the validator itself is a type class. And you can think of it as essentially a nice name for a function from whatever type I'm validating, type T, to the result model. Okay, so that's going to be, that's sort of the baseline for what we're going to be talking about. Why macros? Okay, in this context. So is anyone here entirely unfamiliar with what Scala macros are? Raise your hands if you are. Okay, there's enough people that it warrants a bit of context. A Scala macro is, in effect, a compile time construct that you can use to modify your code at compile time, or to construct code at compile time. So what this means is, if, for instance, back in the day with Java or .NET or anything really, you used to, for instance, define your database schema or some sort of interface description language like IDL. Okay, and you used to build stuff based on top of that, result sets in C# or you know, bean types or schemas with Hibernate or basically anything of the sort. What you used to have is you'd have a language in which you define these things, and then you'd have a build step that would take the description in that specific language and generate actual Java or C# or whatnot code on top of that. Okay, and that's literally part of your build flow, and it's separate from your code. Now what macros allow you to do is they allow you to do that from within Scala code, within the same life cycle, build life cycle phase that your actual code resides in. And you can do a lot of interesting stuff. You can basically take code, modify it, transform it as part of your compilation process. I hope it will become a bit more clear in a bit. So for instance, in this case, what we have is a definition of a validator over the type of person with a bunch of rules. And if you've paid attention, you can tell that there's two things that are sort of not present in this type of code. The first thing is there's automatic description generation. Okay, if you've noticed the failure message that I've had in the earlier example, it said that the description for the property that failed validation was first name, and that's a string. Now here, I don't have a string, right? I don't have anything that tells the compiler, tells the Accord, the data validation API, that the rule that deals with first names should be described by the string first name. So that's automatically generated, and that's something that unfortunately within the confines of the vanilla Scala language and Scala type system, you simply cannot do. You need some sort of way to introspect into the code, to look into the code and figure out that the description for that rule is first name or last name or really anything of the sort. So for that, you need to actually look at what the compiler sees. And that's what macros are useful for. The second thing that the macro transform in Accord does is it adds an implicit AND rule. Okay, the result of the transformation for this thing is not actually an imperative code block that tests this, does something, tests the other rule, does something, and so on and so forth. Instead, what it does is it generates a full-blown validator that has a number of clauses in it and are all wrapped in sort of an AND combinator, which is something that I hope, you know, if anyone did not get from that description, I hope will make sense a couple of slides ahead. So macros give us the ability to introspect into code at compile time, modify it, transform it, do interesting stuff on top of it. Before we actually get into the nuts and bolts of things, you should realize that first off, macros in Scala are still marked as experimental. The fact of the matter is that they've been around since Scala 2.10, so for the last couple of years, are still considered experimental, but are not really. I mean, until Scala Meta comes along, which is a long-term project that is being discussed in another room as we speak, and there's no release date on that. So the API and the mechanisms for using macros, although marked experimental, are actually rather stable. Okay, macros written a couple years ago still, generally speaking, still apply today with Scala 2.11.6 or any new version of Scala. So that's not actually expected to change anytime soon. The second thing you need to realize is that dealing with macros, or rather dealing with any sort of metaprogramming facility, is hard. Okay, and you're going to see how hard as we go through the presentation. So in order to sort of condense something that will hopefully give you a good idea of what these things look like into 40 minutes, I'm going to ignore a lot of small details that if you actually go through the motions of trying to implement a macro, you're going to run into, you're going to Google, you're going to figure it out, so it's not worth the time. And I'm going to simplify a few things that the library actually does so that the explanations actually make sense within the confines of this 40-minute talk. But yes, it is difficult. Okay, don't expect anything to be easy for this talk. So, macros start with abstract syntax trees. And abstract syntax trees are really what the compiler sort of does with your code before it turns it into bytecode. Okay, the first thing that the compiler does with your code is it reads it in. Okay, you have a Scala file, it's just a text file, it's a bunch of strings, right? You need to read them in, you need to parse them, you need to make sense out of the Scala code that is in your in that text file. And the intermediate representation that the compiler sort of builds as it parses your code is called an abstract syntax tree. Abstract syntax trees really deal with two things that are structure and semantics. So structure, or rather, structure is about semantics, and then there's metadata, which I'll cover in a second. The structure is what your code does, right? If you have a class and that class has a method, there's an inherent structure to that. Okay, the definition of the method is enclosed within the definition of the entire class. Okay, so it's all about structure. The semantics are derived from the exact types of node within that tree. So a class definition has a certain type of node within that syntax tree, whereas a method definition has a different type of node. An expression would have yet another type of node. Also, these trees may or may not contain metadata. So if you've seen Martin Dursky's keynote yesterday evening, he talked about tasty and basically about typed ASTs. Okay, you can consider these typed ASTs to be abstract syntax trees that are annotated with additional information that the compiler figures out as it parses the code. So such metadata may include types. Okay, literally, if the compiler infers a type for an expression, that is an annotation on top of the abstract syntax tree. And this annotation may or may not exist depending on the compilation phase that you operate in. These abstract syntax trees are embodied in the Scala Reflection API. And unfortunately, until Scala Meta comes along in its first production version, these trees are mutable. Okay, so that means that if you get an abstract syntax tree from the compiler and you modify something in it, then it actually gets modified. You don't build a new version of the tree with your modifications, you literally work on top of the tree that the compiler sees. This does not have too many ramifications, it's just a subtlety that you need to keep in mind. So what do ASTs look like? Okay, what do I mean when I say abstract syntax tree? Right, let's consider this very, very simple definition of a method called method, and it takes a parameter called param of type string, and it does something with it. Specifically, it transforms it to uppercase and returns the uppercase string as a result. So each part of this expression is its own tree. If we focus, for instance, on the result of the computation, okay, param.toUppercase, what the compiler actually sees, what it parses that expression into, is an apply node. And an apply node is, as its name implies, there's something, okay, there's some object, and you apply a function that exists within the context of that object onto a set of parameters. So for this, so in this case, you'd have an apply node. An apply has two sides. The thing that you start off with, okay, the method that you actually apply, and the set of parameters. In this case, the toUppercase method does not have any parameters, so the parameter list is empty. That's the empty list down there. And the thing that gets applied is the method to uppercase within the string. Okay, so the tree needs to, the tree that the compiler constructs needs to contain all of that information in order to make any sort of sense at compilation time. Different parts of the same expression are the actual definition, the formal definition of a parameter that has its own tree. Okay, so that's a value def. And a value def gets a set of modifiers, which could be visibility modifiers. You could say that it's private or protected or whatnot. It does not make sense in the context of a method parameter, but it's really the same tree node type that you would use for a val definition within a class or a trait or a code block, just about anything. It has a name, and it has a default value potentially, and it has a whole bunch of stuff. Okay, so all of that gets essentially boiled down to an abstract syntax tree. And most crucially, the whole thing is also a tree that comprises those two subtrees that we just discussed. Now, you don't necessarily need to know the exact details of what nodes exist within the confines of the Scala abstract syntax tree definition. There are a number of such types that you're going to have to find out about sooner or later if you're going to deal with macros. What's crucial about this is to realize that everything boils down to a tree. And when you deal with macros or any sort of metaprogramming, really, you deal with trees. Okay, so going back to def macros. Okay, def macros are really the only type of macro that is fully supported within both Scala 2.10 and Scala 2.11. There are other types of macros, but def macros are considered to be the only canonical, fully supported set of macros within the Scala language. Anything else, you'd require either a compiler plugin or you need to work under a certain set of constraints. So what a def macro is it looks and it acts like a normal method. Okay, it has the signature of a normal method. So for instance, in this example, we define a method called radix. Okay, suppose I wanted to give you a way to embed numbers within your code base that are defined in any sensible mathematical base. Okay, not just hexadecimal and decimal numbers and floating points, but also, say, binary numbers or octal number representations for whatever reason. And I want to do this at compile time. Okay, I want to give you the ability to say, I have this number here that's a number in a certain mathematical base, and you get back a constant that has the right value to it. And it all happens at compile time. So this definition gives you the signature, and you could fairly easily implement it at runtime. What def macros give you are the ability to sort of have compile time expansions for method calls. There are two fundamental differences between a def macro and a normal def. One is it's invoked at compile time as opposed to runtime, as discussed. And the second is it operates on expression trees or ASTs as opposed to values. Right? When you invoke a method at runtime, okay, you bind a certain value to that parameter. Okay, if, for instance, I called radix with an expression that evaluated to some string at runtime, that expression actually gets evaluated, and the value of that computation is placed as the parameter value when invoking that method. Okay, when you do it at compile time, what you actually get is the code that is placed at the method invocation point and gives a value to the parameter. Okay, so you work on abstract syntax trees instead of values. Def macros need two things. They need a signature, which you've already seen, and they need an implementation. So the signature is just a method signature, a normal one, the same one that you've written 100 times over the last week. And you annotate the method signature with the keyword macro, and you give it an implementation. Okay, so to define this radix macro, I would have the method signature, and I would say that the implementation for this method is implemented by the macro implementation called radix impl for implementation. The implementation itself looks like this. Okay, this is where things actually start solidifying into actual code. If you take a look at the static's impl definition, it's also a method definition, and it needs to be in a static context, and typically an object of some sort. And what it really does is it takes the method signature, takes the values, it wraps them in something that basically says, I wish I had a laser pointer, sorry. If you look at that S parameter, it's the same S parameter as above, except instead of taking in a value of type string, it takes in a value of type expression of string. And an expression for a macro basically means, give me a tree whose type is known to be string, whose type evaluates to a string. And that's what you start off with. Okay, so you take in an extra parameter list that gives you a context. I'm going to cover that in a second. And you take in the same set of parameters as the formal method signature that is visible to the actual code, but each parameter, instead of having its normal type, takes in an expression of that type. Similarly, you return a tree. Okay, what the compiler does when it comes up to an invocation of a macro method, of a def macro, is it takes the code that comprises the parameters, feeds it into that macro, takes the resulting tree and just plugs it straight into the resulting code. Okay, so your return type must also be an expression, must also be a tree whose type is known to evaluate to, in this case, a long. Okay, so there's a very clear symmetry between what the method signature looks like and the def macro implementation signature looks like. It's a one-to-one mapping. Okay, and as mentioned before, for the regular method signature, it deals with values, whereas for the def macro implementation, it deals with abstract syntax trees. So all of this gives us the ability to deal with trees. We still need some context. Okay, so what's in a context? When your macro actually gets invoked, gets evaluated, okay, somewhere in your user's code, you're gonna have that call to radix. And there's a position to it, okay? There's a position within the code base in which the macro gets invoked. So it gives you the enclosing position, the enclosing context. It gives you a whole bunch of nice facilities for instance, because this is all done at compile time, you may want to emit compilation warnings or compiler errors. Okay, so the context object gives you those facilities. It gives you logging, it gives you a whole bunch of nice stuff. Okay, but the context basically is your entry point into the world the compiler sees as it invokes your macro. So all of these things give us the ability to define compile time code transformations, and for the next 20 odd minutes, I will hopefully show you an example of how that's actually done. Okay, so just to get started, okay, just to put things in context, this is the code we started off with. Okay, there's the person validator object, and the validator, that validator over some type of person, that's a method. Okay, that's a method call, and that's the macro application. Okay, so the user of the Accord library writes code that looks like this. The Accord library actually has to provide the implementation for the macro, the runtime, the compile time code transformation that happens when that validator method gets invoked. So we have the whole code block, that's the macro application, and we have that set of rules that reside within the provided code block from the user context. So the validator macro, what it basically does is it takes each validation rule and it rewrites it. Okay, it needs to figure out what's going on within each validator rule, generate some sort of description, and then rewrite the rule so that the description gets attached to the resulting code that actually gets compiled into the user code base. And it needs to take all of these rules and aggregate them within an AND combinator, within some sort of mechanism that says, you know, all of these rules need to apply. And these are the two things that the macro does. So the signature for this macro specifically is, I have this I have this diff, this method diff called validator, and a validator operates over some type T, which in the earlier example was a person. It takes in a code block. Okay, that's where the actual rules are defined, and it's just a function from T to unit because we don't really care what the resulting, there is no computation there, right? It's all a declaration of validation rules. So we don't really care what the result of that is. And it returns a validator over the type T. Now this is implemented by the macro. Okay, that macro resides in an object called validation transform, and we just told the compiler that this method is actually a macro diff that's implemented by this apply method below. The only thing that's different from what you've seen before is that if I take a type parameter, at compile time, I need the type information that the compiler gives me for that type T. Okay, it's a generic macro. It operates over any type. I need some information about the actual type that's at play. So that's what the weak type tag is for. Any questions so far? I've overwhelmed you already? I hope not. Because it only gets worse. Okay? So far, we've just discussed sort of the envelope of the whole thing, right? How the whole thing ties together to data validation. Now we get into the actual nuts and bolts of what the macro does and how it operates. So take a deep breath and let's get started. Really, in terms of what the macro does, it's it's just 4 steps. Okay, I search for a validation rule within the block I was given. I process that rule to figure out things like, what is being validated, what is the description I need to generate, and what is the validation. Basically tease apart the various bits and pieces that comprise a validation rule. The 3rd step is to generate a description, and the 4th step is to rewrite the rule into something that makes sense in the context of data validation. And let's focus on each of these separately. So to search for a rule, the first thing I need to know is what it is I'm searching for. Now, in the context of a chord, a validation rule is an expression that is basically a sub-validator, right? The validation rule itself is a validator over the type of whatever it is that it's validating. So if I have a rule that says person.firstname is not empty, that rule actually evaluates to the type validator over string, because the thing that I'm validating, p.firstname, is a string. Okay, so what we do is we need to take in the tree that represents the code block with all those validation rules, and we need to pattern match. Okay, we need to recursively look for any subtree that has that particular type. When we have a match, okay, when we found a validation rule, we need to apply some transformation over it. And the way we encode this is a partial function from tree, which is the Scala Reflection API concept for an abstract syntax tree, to some type R. Quick overview of what working with ASTs looks like. Okay, this is a helper function. It doesn't have any logic that has to do with what my actual macro is trying to do. It's just a utility function. Okay, and what it does is it takes in a tree. Okay, this is what I'm searching over, and it takes in a pattern, which is that exact partial function from tree to R. The way this is encoded is that if the partial function is defined for a given tree, it gets applied, and I don't proceed with I don't recurse further into that tree. In order to implement that, first of all, I need some intermediate data structure to actually collect the results of those partial function applications, which is called found. It's just an empty vector to begin with. I use something that's provided by the Scala Reflection API called traverser, which is basically a very simple abstraction that recurses over abstract syntax trees in a very, very simplified manner. And wherever I am in the tree, I ask the question, is this partial function defined for my current subtree? If so, I apply it, I take the result, I add it to my intermediate data structure, I add it to my found list, and move on. If not, I recurse further deep into the tree. I basically traverse the tree depth first, and hopefully find my matches. And then eventually I return that list of found constructs. This allows me to, if I can encode a rule that says, give me back all of the bits and pieces within that code block that have the type validator over whatever type, then this utility function allows me to search for them. And that's exactly what we're going to be doing. So the first thing we're going to do is we need to define, you can flat out ignore those first two lines. That ties together the rest of the steps here. The interesting bits are that in order to find rules, I need to get in a body, okay, the body of the validation code block that I was given at the macro invocation, and I need to return a sequence of rules. In order to do that, the first thing I do is I ask the compiler for the type of specifically the existential type validator, or rather, sorry, the wildcard type validator, okay, because I don't really care what every given rule deals with. I don't care that you have a rule for first names that operates on strings. I don't care that you have a rule for age that operates over integers, right? I'm looking for all of those rules within the validator block. And then I collect from pattern based on the body I was given, and I just look for a subtree where the type for that subtree is some subtype of the validator class. This gives me the list of rules. Now for every rule I encounter, I do some processing on it. That's the next step. So what do I do once I've found a tree that represents a particular validation rule? First off, I lied a little bit. Okay, the user writes this, but in practice, because it's a Scala DSL, there's a whole bunch of implicits and a lot of very nice things that happen behind the scenes. What the compiler actually emits is this thing. Okay, there's the DSL entry point, the extension method, if you will, is embodied in a class called contextualizer, which is a silly name, I know, but it's the only one I could think of. And this is the code that actually gets emitted by the compiler. Now, this actually gives me the ability to break down a rule into its two constituent parts, which is p.firstname is the object under validation. Right? For this particular rule, what it deals with is p.firstname. And there's the actual validation rule, which is not empty. Okay, so because of the DSL, I have a nice entry point into my code that I can look for. I can basically look for applications of the contextualizer class, implicit class. So this is what it looks like, and this is effectively an apply node. Okay, I take the first name, I feed it into the constructor for contextualizer, I use the is method, and this is everything that I'm looking at. Right? If we break this down into the actual abstract syntax tree that we're going to see resulting from the compilation, it's going to look something like this. Okay, there's on that right side, I'm using type apply because contextualizer is also takes in a type parameter. Okay, so it's contextualizer of string. The middle apply node is the constructor call for contextualizer. So it takes in the contextualizer type, and it takes in p.firstname, or the tree that represents p.firstname, and it builds that into something. And then it uses is, it applies the is method on top of that. So all of this winds up being a tree. And I can use that tree structure to start breaking apart the validation rule and extracting useful information from that. So this is what I'm interested in. The first thing I'm interested in is the object under validation, because p.firstname is where I can start looking at the user code to generate the description. Okay, generate the description for violations, for anything that did not properly get validated. Now, I don't really care about the contextualizer thing, right? That's just a mechanism that's very useful to me because I can look for it, but it's not what I'm interested in. What I'm interested in is p.firstname and the subtree that represents it within the parsed code. Now, how do I get at it? Well, looking at the whole subtree, basically, I don't really care about the type. Okay, like I mentioned before, it may be a rule about a string or an int or a list or just about anything, and I don't care. More importantly, I don't care about anything that is a subtree of this select. Okay, this select is actually what I'm interested in. This is the root of the subtree that gives me something I can use to describe the object under validation. So I don't care about those other things as well. I just need to get at what is abbreviated to be OUV, or object under validation. So I can literally pattern match. Okay, I can take in a tree and I can pattern match over it with straightforward Scala pattern matching, right? I can match over it, I can build a partial function to match over it, and I pretty much write down this tree as it is. Okay, I generate a pattern that represents the tree I'm interested in, and I can extract stuff from it. So in this case, this object under validation at the rightmost side, that's what I'm interested in. So I just write this down as is, and then I can actually use it. Okay, I have this process rule function. It takes a subtree. Okay, I've already found a rule. I've already found a tree that has the type validator over some type. Okay, and I know that it's a validation rule, and I can tease it apart. So I use a second utility function called extract from pattern, which is essentially the same as the difference between collect in a normal Scala collection and find. Okay, so, or map as the case may be. And I feed it this pattern, and then I can break my tree apart and just take in the subtrees that I'm interested in. This allows me to build an actual rule. Okay, this allows me to build a domain object within the macro implementation that lets me deal with only the small bits that I'm interested in, which in this case are the object under validation and the entire subtree that represents a particular rule. If I could not find such a pattern, I want to abort the compilation, because this means that basically the user did something somehow that I did not expect, and I don't know how to deal with this. Okay, so I want to abort the compilation with a compilation error that says something along the lines of, hey, at this position you did something and I don't know what to do with it, so you're on your own. So that's what abort does. Any questions so far? Okay, hopefully this made at least some sense. The next thing I want to do is I want to generate a description for my validation rule. So how do I do that? Okay, if we started off with p.firstname and we want to generate a sensible description for that, basically this is a field accessor, right? This is a very simple expression that as humans we can very simply look at and reason about. We can say, okay, if I take in a sample object called p and I'm validating p.firstname, then a sensible description for that would be first name, would be the name of the property that is being accessed. So for this very simple expression, what we need to do is we need to consider the prototype of the function that we were given. Okay, if we go back to what the validator macro looks like, okay, it takes in a code block. It takes in a function from t to unit, right? That has all the validation rules inside it. What is the name that the user elected to give t? Okay, I'm gonna go back a little bit until I can blah 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 blah. Okay, I have a validator over a person, right? It takes in a function from person to unit, and the user, when calling my macro, gave the person the name p. And I can use that because what I get in is the whole abstract syntax tree representing that code block. Okay, I can figure out what P is, and then if I can figure out what P is, I can break apart P.firstName to say, okay, P is just a sample object. I don't need that. No one cares about it. It's not part of the description. First name, on the other hand, is a property accessor. That's what I'm interested in. So that's exactly what we're going to be doing. Moving on a little bit, sorry about that. Okay, this here is the little subtree. Okay, P.firstName is a select abstract syntax tree node that on its left side takes the identifier P, and on the right side takes some term name called first name. Okay, so that's what I'm interested in, and if I have both that and the function prototype, I can match them. And actually have the function prototype. If I go back, way back to the macro definition, to the implementation signature, okay, I take in an expression that gives me the syntax tree for the code block from T to unit. Okay, it gives me all of these validation rules. So to extract the prototype, I just need to break it apart. And I also do that with pattern matching. Okay, this is a function node that takes in a set of parameters. I know I only have one because that's what my signature does. Okay, so I just give it a name. I call it prototype. And then I also can, on the fly, get the body in. Okay, so I just take the tree I was given, break it apart, and now I have access to both. Now, the prototype is, as I mentioned before, it's a formal parameter definition. It's a valdif. It's a specific type of node. And I know that in advance, so I can use that to my advantage. In other words, taking a validation rule, okay, I have this prototype, which is a value definition, okay, that defines the parameter P, and it has a name. The name is P, so I can just use that. And then I can break the rest of it apart. Okay, I have this select that I showed you earlier with a very specific identifier. Okay, and I can just use that to extract the actual, the actual property accessor and use that as a description. And then I just call the string on it and I get it back. What I get back from this for P.firstName is basically first name. I get back the exact string I was interested in. So this is a whole lot of mechanics to go through just to get at the simple description, which is exactly what I mean by macros are hard. Okay, they're not necessarily hard to grasp conceptually, but actually working with them can be a bit daunting. But it is what it is. Okay? If you want the benefits of compile time code transformation, you need to pay the cost of reasoning about what the compiler sees. The last thing we need to do is rewrite the rule. And what do I mean by rewrite the rule? So far, what we've done is teased it apart and generated a description for it. Now we need some sort of way to add the description to the rule. And there's a second thing we need to do is, if we're constructing a validator over the type of person, and it has a bunch of rules in it that apply to different fields for that person. Okay, we have a first name field, we have a last name field, maybe we have an age, an address, etc., etc. And we want to wrap all of these different rules in an AND combinator. Okay, we need to take each and every rule, and each rule may be a validator of string, and we need a way to lift that so that it validates an entire person. And once we have a whole bunch of different rules that apply to a person, we can then just stick them in some sort of AND combinator that we already have within our library. So in this case, what we're going to do is we're going to generate an abstract syntax tree. And fortunately, generating abstract syntax trees is actually typically way easier than breaking them apart because you have something called QuasiQuotes. So a very small digression. Okay, all of this is the abstract syntax tree for the expression x plus y. Okay, this is a whole lot of code, right? If you had to write this manually, you'd be sad. Look at me, I'm sad. Okay? Seriously, I actually had to write shit like that for actual code, not just x plus y. And it's depressing, and it's error prone, and there's a whole bunch of things you can get wrong. And you don't want to do that. So thanks to the efforts of two heroic Scala community contributors, namely Daniel Sheblin and Eugene Burmako, who are actually at the moment talking about Scala Meta at the other room, we can do this. Okay, using QuasiQuotes, which are built into Scala 2.11 and can be added as a compiler plugin to Scala 2.10, we get a string interpolator that lets us basically write code-like strings, including the ability to stick stuff into them, as I'll show you in a second, that just saves us the trouble of having to break down the abstract syntax trees by hand. Okay, so we don't have to write all of this. We can just write that little bit that's on the right that's significantly easier to read and maintain. And that's the way it ought to be. So, two things you can do with QuasiQuotes. The first thing you can do is splice trees. Okay, so whereas you'd have to construct an entire abstract syntax tree by hand, now if you have an expression of type string or even just a raw tree, you can use the string interpolator and just stick that tree as part of the resulting code, which is incredibly useful, as you'll see in a moment. The second thing you can do is use it for pattern matching. Now, the reason why I took you through this insane journey of dealing with abstract syntax trees to begin with is because they're endemic to macros. Right? If you're going to be working with macros, you will need to know about abstract syntax trees, and you will need to know what they mean and how to work with them. You can save a lot of work doing these things with QuasiQuotes, and you probably should, but it's not going to save you from having to understand the fundamental building blocks of what the compiler sees. Okay, so you can use QuasiQuotes for pattern matching as well, which would make all of the code I just showed you a lot simpler. But not simpler to understand, merely simpler to read and write. Okay, so with QuasiQuotes, I can rewrite rules very simply. So specifically, if I have this rule above that we started off with, we want to do two things. We want to add the description that we generated, and we want to lift it from a validator over a string, because first name is a string, to a validator over the person object. Okay, so this is the resulting code that we want to have. If you remember way back to the third slide, a validator is essentially a function from T to the result model. Okay, so we can just define it. Okay, we have this new validator of person, and it's a function, so it needs an apply method, right? The apply method takes in a person object, and what it does is it takes the validation rules and it applies it to that person in a very straightforward manner. Now, the way the Accord DSL is constructed, it's specifically constructed to make this step very, very simple. Okay, contextualizer over p.firstname is not empty, actually evaluates to a validator over strings. Okay, it just gives you back the same validation rule outside of the context of p.firstname, right? The validation rule is not empty. I don't really care what it applies to. So I just take advantage of the fact that I'm in control of both the DSL and the macro itself, and make this step really, really easy. So the validation rule, yes, I'm sorry? Yes. No, what I mean is, this is not a quasi-quote. This is an example of what the result of a rewrite would look like. Okay, at this point I haven't actually done anything. I'm just giving you an example of what the result of rewriting that specific rule would look like, what the resulting code should be. Okay, so with this in mind, what I can now do with quasi-quotes is simply this. Okay, this makes it way easier. Now consider that without quasi-quotes, the amount of code that this turns out to be is about 7 or 8 printed pages of Scala code, which is not fun. Conversely, with quasi-quotes, I can just pretty much do this. I can take all of the little trees and descriptions and all that stuff that I generated on the fly as I was doing my building up my macro, and just stick it in there. Stick it in the quasi-quotes, splice it in, and it's that simple. Okay, just rewrite the code to be what it should be. Last but not least, we're done in exactly 1 minute, and then you can beat the crap out of me outside if I've made your head explode. So the last thing that we need to do is we need to take all of those rewritten rules and wrap them in an AND combinator. Okay, so the way this whole thing looks like ends up being, I have the macro implementation signature above. I tease apart the prototype function that I was given so that I can access that P symbol, and I get the body as well. Take all of the stuff we just discussed, imagine that it's there in the middle, okay? And the bottom line is, what I do is, I find the rules from the body, I take each and every rule and rewrite it, then I get in a list of rules, and then I use a second very nice feature of QuasiQuotes, which is the ability to take a sequence of trees and just feed it into a variadic function. So this AND combinator just takes a whole bunch of combinators over the same type. Okay, if I have 3 different validators over the type person, I can just feed them as parameters into the AND combinator and get the AND semantics over each and every one of them over the same type. And that's exactly what I'm doing with that last rewrite there. And the end result is I need to wrap that tree that I just generated with an expression. I need to annotate it with a known type, because that's my return type. Okay, so I just wrap it in an expression that gives me back a validator of t, and that's it, and I'm good to go. And we're done. So, do we have time for questions? Okay, so any questions at this point? Yeah. I'm sorry, I didn't get that. So the question is, would the first part that deals with actually looking at the parse code and breaking it apart be possible and easier with QuasiQuotes? The answer is yes. I intentionally gave you the hard story instead of the easy story. QuasiQuotes make everything simpler. Once again, they make everything simpler to do, not to understand. Yes, whomever. Okay, so the question was, what do macros make possible in this context that would not be possible otherwise? And the simple answer is, looking back quite a few slides at this point. Okay. There is absolutely no way that I know of in Scala. Yes. Okay, there is absolutely no way to reason about this code within the confines of Scala as such, and knowing that that second rule deals with a property called last name. You need to introspect into the parse code to do that. Okay, does that answer your question? Yes. Now this is I'll get back to you in a sec. This is a hell of a scaffolding just to get at the first name. It also on the fly rewrites a very kind of imperative set of rules into a declarative, and you don't want to have to write manually write and parentheses first rule, comma second rule, comma third rule, etc., etc. So that's the second thing that it does. And third, and probably most importantly, is this is a very, very simple example for a validation rule. They can be a hell of a lot more complex. And when they become a lot more complex, it also becomes a lot more difficult to get at those constituent bits of the code without some sort of metaprogramming facilities. The question was, are there ORs as well? There are. I just didn't give them as an example. And is implied because the domain is validation. So whenever you do validation, you always run eagerly through all of your validation rules because you want all of the errors that you've aggregated. There's also OR rules, but those are kind of not necessarily implied in the context of data validation. Right, there was another hand, yeah.
One thing Tom mentioned in your slide that you can't pattern map on your structure of your object validation or the compilation. That seems strange because there's basic ways in which I can express validation.
Yeah. Yeah, so it's a bit of a long question, so I'm not going to repeat it for the camera, but the bottom line is, this is a simplified version. There's actually a lot more behind the scenes kind of magic to properly generate descriptions in the actual library. It deals with things like nested indirections and various expressions and all of that stuff. So this is just a simplified example. Yeah, whomever, sorry. So the question was, if an error occurs during the evaluation of the macro, does it throw a runtime exception or a compile time exception? The answer is it throws a runtime exception that occurs within the compiler. So the compiler actually catches that runtime exception and then gives you a compilation error that says, error occurred during macro expansion, because it doesn't have any more context, so it just gives you a dump of what happened. This is essentially the same as a compiler bug. Like if the compiler throws a runtime exception for whatever reason, you get largely the same output as if your macro crashed. Does that answer the question?
Yeah, but what happens when my object person is created at the runtime? Because I don't know the values of like the first name and until runtime.
Yeah, so the question was, what happens at runtime? Now, there is the distinction, right? The compile time facility is for transforming this code. This declares a validation. This does not invoke the validation. You invoke the validation at runtime. You build the validation up at compile time. That's the difference. Okay, probably time, no more time? Okay, I'm sorry, so catch me afterwards, and thank you for your time.